Good morning, everyone. Thank you, Ian, for a nice introduction. I presented some of the material last month at the NGD monthly meeting, and Xiaochen thought I should give a talk at the all-hands meeting. Okay. We've been working on the stochastic convection parameterization for a while with in the NGD project, and so we have finally got some results that I can share with you. And most of the work was actually the heavy lifting was done by Wang, a collaborator of mine at Tsinghua University. And first, I'm going to give a quick sort of a rundown on why stochastic parameterization, and then show a couple of specifics of what we did, and then followed by some results and a summary. So in GCMs, as we get to higher resolution, and then the quasi-equilibrium hypothesis in conventional deterministic convection scheme is not going to be satisfied very well. By that I mean within each GCM grid box, in deterministic way, we assume that given in a large-scale forcing or atmospheric state, you would have an ensemble of clouds, and the ensemble average would be what the parameterization determines. And as resolution gets higher, however, you would have a non-equilibrium situation. In that case, each realization may produce or a cloud or may not produce a cloud, really depending on how much stochasticity there is in the model. And so the stochastic parameterizations try to pick up this individual realization of a PDF of convective response to a given large-scale forcing. Here's an example from previous studies. One is by Zhang and Randall. In their CRM simulation, they used periodical forcing over several cycles of convection, and then try to see how much of stochasticity there is in the model response. The red line here is I'm trying to get the cursor. The red curve is a response, the large-scale forcing, and the green curve, the blue curves are the convective response. In the upper left corner, the response was averaged over the entire domain for several convective cycles. And what you see is that they are fairly close to each other in each in each simulation. On the other hand, as you start to average as you start to average over smaller and smaller subdomains, then it becomes clear that the standard deviation is much larger as you get to a very high resolution. And similarly, Planck and Craig carried out the simulations, and then when they average the mass flux over a larger domain, the mass flux distribution has a very narrow peak and a narrow distribution. On the other hand, if you average over a smaller domain, then it becomes a much wider distribution. So what this says is that given the forcing, there is a much wider response, a wider range of response if you go to a smaller domain. So based on that, then they developed a Plant and Craig developed a stochastic convection parameterization using some theoretical considerations of statistical mechanics. And here there are two major probability distribution equations. One is the mass flux of a given cloud that produces a mass flux of m. What is the probability of that? And another is the number of clouds within a grid box, the probability of that. So the number of clouds for a given mass flux, that follows the Poisson distribution, whereas the mass flux of a given cloud follows a Boltzmann distribution. So if you combine these two, finally you would end up with an equation for a mass flux probability distribution for a number, for a single cloud. Here we choose a single cloud because for the probability of having more than one cloud, then that becomes a high order term and it can be ignored. So basically, with these two equations, eventually we have this equation, and then this equation determines a mass flux for given for triggering a cloud. Then in implementation we had in Chem 5, we have averaged the domain over, average the forcing over a much larger domain as what Craig and the plant originally planned. But then for consideration of the computational cost in E3SM and also for considerations that the probability, the quasi-equilibrium can hold if you hold it for a longer time instead of over a larger area. So we then just simply implement the rest of the specifics. That is, the mass flux, the total mass flux, or the ensemble mass flux is determined by the ZM scheme, and that mass flux is needed in the probability distribution of the total number of clouds, which is the total mass flux divided by a mass flux of a given cloud. And then the probability is determined whether there is a cloud or not, is determined by a random number. So each time we draw a random number and compare that with the probability of a mass flux within a mass flux bin. If the probability is greater than that random number, then there is a cloud. If it's smaller than that, there is no cloud. So after we have done all these bins, then we sum up all the total mass flux from each of these clouds that were triggered. And then we determine the total heating and moistening due to the entire population of the clouds. So we put this into E3SM or EAM in the atmospheric model and ran that for on the AMIP configuration, around that for 6 years. And the first year was thrown away, and the rest of the last 5 years were used for model analysis. So we have two simulations. One is a standard control run, and the other is with the stochastic parameterization. Everything else identical. So the control run shows, this is a precipitation distribution of the last 5 years, and for the control run, and the middle is experiment with the stochastic parameterization, and the bottom is from GPCP. And the major characteristics of the precipitation distribution remain the same. You can see the ITCZ and then the ITCZ of the Indian Ocean, etc. And the distribution or the contribution from the convective versus large scale compared to trim Again, they're similar, and they share both a similar strength and a weakness. For instance, the large-scale precipitation is still underestimated compared to TRIM observations. This probably gives you a better view by looking at the difference between the experiment and the control. There is a bit more precipitation of the Western Pacific warm pool and along the ITCC, and but then slightly less precipitation in the Amazons, and that is mostly from the convective part, and the large-scale part. There is a bit of increased precipitation over the Western Pacific. So now comes to the PDF distribution of the daily precipitation. We saved the data on daily averages and then looked at the PDF of precipitation intensity. The horizontal axis is rainfall intensity, and the vertical axis is a log scale the frequency of occurrence. And the black line is from TRIM observations, and the blue is from the control. And this is well known that in the low intensity part, the model is way overestimated the frequency of drizzles, and in the high precipitation part, then the model is underestimating that. By putting the stochastic parameterization in that, it's a much better agreement with the observations and with increased frequency in intense precipitation and decreased intense frequency in the drizzle part. And if we break this down into convective and a large scale, you can see that the reduction in the drizzle part mostly comes from the convective part. As you can see, there is very little difference between in the large scale part precipitation. But on the other hand, the increased intensity, the intense precipitation, both the convective part and the large scale contribute. And when we first put it into E3SM, we were actually a little bit disappointed that it didn't improve as much as what we saw in CAM 5. In CAM 5, the red line essentially sort of falls on top of the black line. So we did a little sensitivity test by looking at the 30-level model of E3SM. And now what we see is that indeed the green is for the 30 level and the red is from the previous slide, that is for the 72 level. And now with the 30 level, both the decrease in the drizzle part and the increase in the intense precipitation part get close to the TRIM. So there is some sensitivity in terms of model vertical resolution. And then in last month, NGD talk, people were asking how do the PDFs look at the individual regions. So I then looked at a few regions that the first on the Amazon and the Western Pacific. This is the Indian monsoon region. And then Western Pacific Maritime Continent, and then the SGP side, as well as Eastern China during their monsoon rain season. And as you can see that overall, in most of the regions, there is improved PDF distribution to varying degree. For instance, of the Amazons, improvement is quite substantial, and over the Western Pacific, the intensity in the frequency of the intense precipitation is improved, but not as close to the TRIM as what we saw for the tropic averages. And then of the Indian monsoon region, the drizzle part is improved, but the intense precipitation part is not by as much. And then over the Maritime Continent, it's improved across intensity, rainfall intensity spectrum, whereas over the SGP, that's I think one of the reasons is that over the SGP summertime, although it's a convective regime, a large part also comes from the large scale, so the improvement is sort of about half, and over the Eastern China monsoon season, and then again the low light rain part is improved substantially. And so then we look at the frequency reduction of convection in over the geographical distribution. So again, that's a experiment minus control. This shows the frequency of convection, convective precipitation between the experiment and the control, the difference. There is a substantial reduction, and then the bottom part is for the precipitation intensity that's less than 20 millimeter per day. So this is more like a subset of that. And again, most of the reduction is in the light rain part, and the reduction of frequency is by as much as like 20–30%. And then we also looked at the intraseasonal variability here. The variability is bandpassed by 20 to 80 a day bandpass. And this is a CMAP, sea and Arkan precipitation, and the right is trim. And there is a substantial amount of intraseasonal variability in observations. On the other hand, the E3SM control round does not have as much, and then we see that by including the stochastic parameterization, the intraseasonal band of variability also increased. And then if we look at the 30 level, it is increased even more. And then in addition to intraseasonal variability, we also looked at the Synoptic-scale variance, and this is bandpassed by 2 to 9 days of the bandpass, filtered by 9 days of the bandpass. And the trim has a lot of variance here, and again, comparing the EAM model, it's much weaker in the synoptic scale variance, and then compared to the stochastic parameterization after including that does have enhanced synoptic scale variance as well. So so far I've showed the variance and the intensity PDF, and then now we look at the mean distribution. The left is a column water vapor, the right is a liquid water pad. And then top is control round. The top is a stochastic parameterization. The bottom is, the middle is a control, and the bottom is a difference. In terms of column water vapor, there is not much difference. There is a mean of 0.28, which is like about 1%. And there is a bit more over the ITCZ region, but less over the Indian monsoon region. And then in terms of liquid water path, the control, the stochastic part seem to be less compared to the control by about a little bit less than 10%. And again, mostly they are over the ITCZ region. Okay, in terms of shortwave and long-wave cloud radiated forcing, again, the difference is quite small. Again, the top is from the stochastic parameterization, the bottom, the middle is control. Okay, and shortwave is compared to the observations. I think the observations about 48 to 51 something. We sort of underestimate the observations, and the stochastic part becomes even less by about 2 watts per square meter. And in terms of long wave, the difference is very small. And then in terms of a cloud distribution, we have now more high clouds over the ITCC region, and not much a change of mid-level clouds. But then we have the decreased low-level clouds, mostly over the open oceans, and where the climatological low cloud is sort of located, but slightly shifted towards the coastal part. So there is a slight increase over the coastal part, but then a slight decrease of the open oceans. So this last figure shows sort of summarizes the mean comparing the observation, comparing the experiment with the control, and I also put the CAM5 model here for comparison. And then the black is from CAM, and the blue is from the control, and the green is from the stochastic. As you can see that most of that the blue and the green fall on top of each other. So in terms of mean, they're about the same, and the only noticeable deterioration or the degradation is sort of land rainfall. That's 3. So there is the sort of degeneration of the simulation. Okay, and here's a summary of the talk. Incorporating a stochastic convection scheme improves the PDF of precipitation intensity, and largely alleviating the too much drizzle and too little intense precipitation part. And the reduction of the drizzle mostly comes from the reduction of occurrence of frequency. And the frequency of convection with low precipitation is reduced globally, not just over the tropics. And the intraseasonal and synoptic-scale variances are also improved. And then the mean states do not change much, which means if and when this is incorporated into E3SM, then probably extra tuning should not be too much work. Okay, thank you very much.